today's video, we're going to go through estimating a spatial regression in GeoDa, and then I'm going to talk to you about why doing a spatial regression in GeoDa is not a good idea. It's okay if you're doing some exploratory work, but you can't just stop there. As always, you can download this handout that I'm going through and the data from my website, berkeyacademy.com, or spatial.berkeyacademy.com is better. I'm going to name this handout 5geodaregression.pdf in my files list. If you look over on the left-hand side of the page there, I'm going to add this video to the playlist. And of course, you can also download the data set that we're going to use. It's the same one we created in an earlier video with the alcohol data and the counties of North Carolina and Virginia. So let me just give you a disclaimer before we get going here. I'm going to be talking a lot about GeoDa, and if you've watched my previous videos, you know I'm a fan of GeoDa. It does a lot of things very, very well, but I'm going to be doing a lot of criticism about how it handles spatial regression. But I want to just make sure to be clear that nothing in this video should be considered a criticism of Luke Anslin or his team. This tool was created many years ago. I'm not putting this disclaimer here because I'm scared. I'm doing this out of the utmost respect. I love Luke Anslin. I love what he has done for the field of spatial econometrics. And the GeoDa tool was created years ago, and it hasn't been updated with the latest and greatest. So those are where the criticisms are coming from. So let's go through very briefly what GeoDa does and what Luke Anslin's specification method at least was when he created these tools. So the Anslin method basically says, first, let's run OLS, run an ordinary least squares model. Then, after you have the estimates for the least squares model, run what's called a Lagrange multiplier test. So what is that? Let's make sure we understand a little bit about what this is telling us. So a Lagrange multiplier test, sometimes people will call this a score test or a RAL test or a RAL score test. Basically speaking, what this is doing is you take your estimates from an ordinary least squares regression and you plug them into the derivative of the maximum likelihood function for a spatial model. So we know what these spatial models look like. We know what the maximum likelihood function looks like. You can take a derivative of it, which tells you for each variable, what is the slope? In other words, how much faster is this model getting better? In other words, the maximum likelihood function is increasing. How much faster is the maximum likelihood increasing as you change the values of the variables? Now, basically, when you're running OLS, you're getting the wrong, quote unquote, estimates for the slope coefficients of the variables, and you're also constraining the spatial parameters to be zero. Years ago, when Luke created these, it was much, much easier to do a Lagrange multiplier test rather than actually estimate the spatial model. It's a lot faster, it takes a lot less computational power. So I just have a little visual aid over here on the right hand side. So imagine this is the Lagrange multiplier function, and if we plugged in our values from our OLS estimation, what we're doing is we're looking at what is the slope of this likelihood function curve. If the slope is very steep, what that indicates is that we could get a lot of improvement from running the spatial model. The likelihood function is going to increase very quickly if we estimate the spatial model instead. However, if we plug in our values from our OLS estimation and the slope is very flat, that tends to suggest that we're not going to get a lot of increase in the fit of our model if we run the spatial model. So why bother, in other words? So that's basically, in a nutshell, what these Lagrange multiplier tests are doing. So it's basically a chi-squared test, and the null hypothesis is that these slopes are zero that we're looking at, that we're not going to be getting much improvement. So if we reject that, we're saying that those slopes are pretty steep and we should probably estimate the spatial model. Let's go do a regression in JOTA and let's see what it is able to do, and then let's come back and look at some of these details here. Okay, so we have JOTA open here, and I'm going to take our shapefile and I'm going to drag and drop it over here, and that brings up our map. And let's do the steps that you would normally want to do if you wanted to run a spatial regression. Now, I'm not going to claim that this spatial regression I'm going to run is going to make any sense. I'm just going to throw some of these variables in here just to see what happens, okay? So let's specify a weights matrix first. We did this in an earlier video, but let's just create some new ones. So create spatial weights matrix. You have to specify an ID variable, so we'll use say county. Oh, sorry, I can't use county. What did you, we used before FIPS, or FIPS2, okay. And let's just do a queen contiguity matrix, first order. That just means your neighbors, your queen neighbors are counted, but not your neighbors of your neighbors. And let's just click create, and let's save that. And again, I always want to name this so I know what kind of weights file I created in case I ever need to use it for something else. Now let's run a regression. So click up here on regression on this floating toolbar, and let's add some variables. So my dependent variable, I'm going to make sales per capita. This is liquor sales per capita. And let's just throw in some variables that might be useful here. Maybe what percentage of the population is urban, per capita income, distance between each census block group and ABC stores. So this is an average for each of those counties. So I can double click on the variable, or we can click these little arrows over here. And let's just keep it simple. Maybe we'll do, something like unemployment rate. Okay, now we'd probably want a more complete. Let's add one more, the percentage of people that work in entertainment and recreation fields in the county. Okay, so let's just leave it simple for now. And let's use the weights file queen, and let's run a classic or an OLS model, and let's click run. So let's see what we are given here. Just kind of go down from the top to the bottom. Number of observations, dependent variable, the average of the dependent variable. So this is about $65 per person per year that they buy in liquor. Tells us the R squared here, about 43%. So let's go down here and look at these coefficients very briefly. This isn't really what we care about, but suggests positive here. Well, not statistically significant for urban. Per capita income, positive and statistically significant at, say, the 10% level. So liquor is a normal good. People's incomes are higher. They do drink more liquor. The distance between where people live in these block group neighborhoods and the nearest ABC store, negative, as we would expect. The further you have to drive, the less you're likely to buy liquor. You might buy beer or wine instead. Unemployment, positive. So in regions where there's more unemployment, people might drink more. And the more people who work in the entertainment and travel and recreation industries, more liquor is going to be sold in those areas. More hotels, more resorts, things like that, okay? Now, what we really want to look at here are these tests down at the bottom. This is what everybody puts in their research papers. We have the Moran's eye test. So this looks at the residuals from the OLS regression to ask the question, is there any spatial relationship in the residuals? And this p-value being very high says, doesn't look like it. The Lagrange multiplier tests for the lag model or the SAR model. So this is for the lag Y. This is pretty high p-value. Suggests a lag model might not be appropriate. But then we have this robust version that has a very low p-value. What should we do? We'll go look and see what Luke Anslin suggests we do with this information. The error Lagrange multiplier test, high p-value, suggests maybe an error model is not the right one. But then the robust version. So what the robust versions are trying to do, because these Lagrange multiplier tests are sensitive to false positives. By that I mean that if you have a model that truly should be an error model, spatial error model, that does kind of look similar in structure in the data generating process to a lag model. And a lag model can very easily kind of look like an error model. So it's easy to get a false positive for these things. Now the last Lagrange multiplier test is for a SARMA model. A SARMA model is kind of a combination of a lag and an error model. Big p-value for the Moran's I for the errors. Large p-value for the lag, low for the robust version though. And the robust version is trying to filter out the possibility that we're being fooled into thinking that it's a lag, but it's really an error. Lagrange multiplier error, high p-value, but a low for the robust version, low for the SARMA. So we're getting some strange results. What direction should we head in here? Let's go back and look and see what Luke Anselin's suggestions would be. So from Luke Anselin's GEODA workbook back in 2005, he says, well, basically ignore that Lagrange multiplier SARMA test, because he says that last test relates to the higher order alternative. That means the more complicated model, basically, of a model with both spatial lag and spatial error terms. This test is only included for the sake of completeness, since it is not that useful in practice. More specifically, in addition to detecting the higher order alternative for which it is designed, the test also has high power against the one-directional alternatives. In other words, it will tend to be significant when either the error or the lag model are the proper alternatives, but not necessarily the higher order alternative. To simplify that and translate that into English, he's talking about this false positive idea, that a SARMA model, if you're testing to see if the SARMA model is right, both lag and error, it's going to want to tell you that, oh yeah, this is the right model, even if it's not. Because it can kind of be tripped. It can get a false positive if either the error or the lag are the right model. So because of this false propensity for false positives, maybe you should ignore that SARMA test. So let's look at this little flow chart that Luke Anselin has in this worksheet and how he suggests that you use GEODA. Run the OLS. We did that. Look at those Lagrange multiplier diagnostics. Is either one of those significant? And they weren't. Right? Remember, they weren't. Let's look at this again. So he's talking about the non-robust versions. So the non-robust versions, 0.188 and 0.896. So no. So neither, or one, or both. So he says if neither one of those non-robust ones are statistically significant, hey, just use OLS. OLS is the right model. Okay. What if we did have one of those that were positive? Then he says, look at the robust. But in our case, it's kind of weird because the robust versions are statistically significant even though the non-robust aren't. I haven't seen that before. Maybe we should change our specification just to see. But in any case, if both of those are significant, he would suggest then just focus on the robust versions. And then if just the robust error is significant, of course, go with the error model. If just the LM lag is significant, go with the spatial lag model. When I was taking Luke Anselin's class, I had a case where both the robust error and lag versions were both significant, and I asked Luke, what should I do there? And he suggested, well, look at the one with the lower p-value in that case. It's not a guaranteed right answer, but it's kind of an intuition that maybe that would be the best way to go. So if the robust LM error had a p-value of 0.01, the robust lag was 0.00001, go with the lag in that case. Now over here, what if just one of those non-robust versions were significant? Then just run whichever one that indicates. And again, he doesn't tell you what to do with that SARMA diagnostic. Now in our case, it would probably make sense, since neither the non-robust lag or the non-robust error were significant, but the SARMA was, maybe we should look at a SARMA model or a related model called a SAR-R. We'll go through those in the next video, where we look at different models and how you need to think about choosing them in more detail and why that's important. Maybe we really ought to look there, but this flowchart doesn't really tell us what to do, except, well, maybe we don't have a spatial model the way we've specified it. And maybe we should believe that, because if you look at this first result here, it just says there's no spatial relationship in the error terms. So let's talk a little bit more about what we just did and what it all means. So GeoDa, when you do those tests, you can go through that flow chart and it will sometimes indicate what you should do. In this case, it told us just go with OLS. That might be the right direction to go, and it might not be the right direction to go. Let's review. So GeoDa itself can sort of handle three different kinds of models. The spatial lag, what some people call the spatial autoregressive model. That's where you have the lag Ys. That Lagrange multiplier test seemed to indicate that's not the right model. It can also handle the spatial error model, where there's no lag Y, but you just have spatial correlation, spatial relationship in your residuals. And it can test for the SARMA model with that LM test that we were just looking at, but it can't actually run the SARMA model. So you can't estimate a SARMA model in GeoDa. Now a SARMA model, let me just very briefly, we'll get more into this into the next video. The SARMA model has lag Ys and also lag residuals, but it's different from a similar kind of model called a SAR-R. This is what Anslin calls a SAR-R. Lesage and Pace calls it a SAC model, SAC model. The SARMA model, the relationship between the residuals is in this I minus lambda W term. In the SAR-R, and it also has the lag Ys. In the SAR-R model, it has the lag Ys, and it has a little bit different relationship in the residuals. Turns out, long story short, the SAR-R has a more global relationship in the residuals, meaning that regions that are farther away, their residuals are going to affect what's going on in our region more in the SAR-R model than in the SARMA model. The SARMA model is a little bit more of a local model, where there's a much stronger effect near it by my close neighbors than by my further away neighbors. We'll talk about that in more detail in the next video, however. So one weakness is GeoDa, if we thought we wanted to try a SARMA model, GeoDa can't run a SARMA model. Other weaknesses. So even though it'll run Lagrange multiplier tests for the lag error and the SARMA, it does not check for any of the other interesting models we might be interested in, like the SAR-R, like the spatial Durbin model, like the spatial Durbin error model. We'll go into those in more detail in the next video. As I said, it won't actually run the SARMA. Another weakness of GeoDa is that you can only estimate models with symmetric weights matrices. You can do these Lagrange multiplier tests for models that have non-symmetric spatial weights matrices, but you can't actually run the estimates for the model if they don't have symmetric weights matrices. So what's an asymmetric weights matrix? K nearest neighbors is often non-symmetric. Non-symmetric means that you might have one region where one of my neighbors is, let's call it county A. So one of my neighbors in the weights matrix is county A because it's one of my 5 closest. But county A, I'm not one of the 5 closest for county A because it has 5 other counties that are closer to it than I am. So I might be kind of an island, sort of an island far away, So when I'm looking for my 5 closest neighbors, I have to look very far away to find my 5 closest, but my neighbors don't have to look so far away to find their 5 closest. That's what an asymmetric weights matrix means. So GeoDa will give you an error if you try to run estimates for a model with asymmetric weights matrices. And lastly, this is another important weakness. When you have a SAR model, it'll estimate the model. Let's go estimate a model real quickly. It'll estimate the coefficients, but it will not estimate the marginal effects, which are different from the coefficients. Let's go estimate a SAR model with the model we were just looking at, and let's talk about this in a little more detail, and then I'm going to end this video, because in the next video, that's where we're going to focus on the difference between the coefficient estimates you get and the marginal effects. But I just want to give you a flavor of this for right now. Okay, so we're back in GeoDa here, and instead of running the classic model, let's do the spatial error first, real quick. Let's run it, and let's look and see what we get. Now, when you run a spatial error test, and this is why you have to really focus on doing all the details of running spatial models if you're going to do this right. Running the spatial error model here, no problem. Everything you see here is correct. There's no problem with it at all. Now, the one problem we have is heteroscedasticity. GeoDa helpfully runs a Bruce-Pagan test here and tells us, whoop, we have heteroscedasticity in our residuals. It looks at the residuals from this spatial error model and sees, is there any extra spatial correlation? It runs like a Moran's eye for the residuals for this spatial error model, and it says, nope, no residual spatial correlation there. So we're good. And these coefficients here, there's nothing wrong with them. This lambda that's negative, even though the probability p-value there is very high, so we can't reject the fact that there is no spatial relationship in our residuals as we've specified this model. These coefficients here, there's nothing wrong with them. You can interpret these slope coefficients as marginal effects. However, let's go run a SAR model, spatial lag model here. Run. Big problem. When you go to look at these coefficients here, the 0.04 on percent urban, the 0.012 on per capita income, the negative 0.64 on the distance between block group and the nearest ABC store, the 4 on the unemployment rate. You cannot interpret these coefficients as being the marginal effects, meaning, well, what if we change the distance between the block groups where people live and the nearest ABC store? Wouldn't that mean that this slope is the marginal effect, that for each mile we increase that distance? Say if we shut some stores down, if we increase that distance by a mile, won't people drink $6.54 less per year? No, you can't interpret these slopes. In the error you can, but in the lag model you can't. Why not? Well, here's this lag parameter, rho, minus 0.141748. The reason you can't interpret these slope coefficients as marginal effects is because of this lag y. Let me demonstrate this in a very simple way for you so that you can see why this is important, and we're going to do this in much more detail in the next video. Okay, when you have a spatial lag model, here is the intuition behind why the coefficients you estimate are not the marginal effects that you should be interested in. As we just saw in our model that we estimated, we had a negative lambda coefficient here, and we had, let's just suppose we were looking at a positive, one of the positive coefficients we had. Let's make this the simplest model with only 3 regions, A, B, and C here. And let's just get a basic picture of what happens when we start changing the values of our x's. So let's look at a simple model with just one explanatory variable. So suppose y, again, is how much people drink. And let's suppose we estimated a model similar to what we just had, but let's just make it easier to understand here. So our y value is equal to, let's suppose this is negative like we had in the other model we just estimated. Let's suppose it's just 0.1 wy. So this means our amount our people drink in our county is equal to minus 0.1 times the neighboring values of how much our neighbors drink plus, and let's just suppose we look at one of these variables, percentage of people who work in the entertainment industry. So let's suppose that's just 4 is our beta, and we're just looking at one explanatory variable, so we can just write this 4 times x, and x is, again, percent people who work in entertainment and recreation, plus some residual, okay? Suppose this is the model that we had estimated. What's the marginal effect? What would happen if we opened up a new casino and 1% more people in our county, let's suppose we're county A, and 1% more people in our county were going to work in entertainment and recreation? What would that do to Y, the percent or the amount of that people drink in our county? Well, this 4 suggests that the amount people drink in our county per person would go up by 4. But that's incorrect, because now we're ignoring this spatial relationship here. So let's trace this through just in a simple matter for about a minute. If this went up by 1, then that is going to increase this by 4. Sure enough, but that's just the first step. What else happens? Well, because our value of how much people in our county went up by 4, what's going to happen to our neighbors? Oh, well, this is our neighbor here, B. Their y is going to be going down by 0.1 times 4. So it's going to go down by 0.4. Now, what else is going to happen? Well, that's going to spill over to C. Since their y went down by 4, their y is going to go down by 0.1 times 0.4. So their y is going to go down by 0.04. But it doesn't end there, because their y went down by 0.04. Now there's this feedback effect where their y is going to go down by 0.004, 0.1 times 0.04. And then because their y went down by 0.4, but then it's going down by another 0.004, that's going to have feedback effects to where hopefully that's enough to get you to see that this value of 4 is not the marginal effect. It's not that simple. So you have to properly calculate in any model that has a lag y, like the SAR model and like the Spatial Durbin model or the SAR-R model, you're going to have to carefully calculate the marginal effects. And this is something that Lesage and Pace in their 2009 book really brought to the forefront, and they started creating some tools to do that. And this is one weakness of GeoDA. It doesn't calculate these marginal effects. The upshot of this is you're going to want to use a package that properly calculates these effects. You don't want to do these by hand, but you have to have a good understanding about when this needs to be done and why you should be cautious about interpreting these coefficient estimates without very, very carefully calculating and thinking about them. One last thing let me mention in this video. Just to make sure that I'm not leaving out anything that the GeoDA team has on their website, let me just show you some other tools they have. We've been using GeoDA. They also have this other tool called GeoDA Space that does build in some other tools for looking at some specific situations that you might want to estimate in models. They also have this Python library called PySal. Even though these build in some more interesting cases that you can estimate, they don't solve all the problems that I was bringing up. In fact, it doesn't solve any of the problems that I was bringing up before. Here is a little list from the GeoDA people's website about some of the things that their newer group of tools, GeoDA Space, can do. And they can do OLS and two-stage least squares. They can do two-stage least squares with spatial lag and error models. They can deal with endogenous regressions. They have some GMM estimation in addition to the maximum likelihood estimation. They have some lag and error models that it can run and handle some endogenous regressors here. But still, the newer thinking that I agree with from Lesage and Pace, that if you're going to estimate models, you want to be able to look at the spatial Durbin models and the spatial Durbin error models as well. You can't do them here. However, in R and in MATLAB, as well as in a package for Stata, you can handle the full range of models that you might want to consider. So that makes learning GeoDa, it's great. It's great for specifying weights matrices, doing some exploratory work, but you can't just stay there. So in the next video, we're going to look in more detail about why you should consider these other models and why calculating the marginal effects correctly is extremely important to more intuition about how that works. And then we'll start a series where we go into R, where we can specify and test a more complete range of these models. So please join me for those videos. If you like this video, please give me a thumbs up. If you didn't, give me a thumbs down. Please leave me some comments about what you like and what you don't like and what you'd like to see done in the future. Thank you very much for joining me. Best of luck.